Okay, good afternoon. Thank you very much for watching this video and tuning into my channel. Please consider hitting that button. Anyway, this is in preparation for another video that I'd like to make on some of the circuits I've built for the LM567 tone decoder. And to properly make that video, I felt I should probably read the data sheet for the LM567. So I don't want to waste a whole lot of time talking, and I guess my intent will be just to cover what I think is critical to understand the chip. For instance, this chip comes in a surface mount type of format, SOIC, and I guess it comes in a reel for a pick and place machine. Well, I just won't be covering this kind of information in the data sheet. I really want to get at information that pertains to the chip itself and how the chip works and functions. This is from Texas Instruments, LM567 tone decoder, revised December 2014. Features 20:1 frequency range with an external resistor, logic compatible output with 100 milliamp current sinking capability, bandwidth adjustable from 0 to 14%, high rejection of out-of-band signals, and noise immunity to false signals, highly stable center frequency adjustable from 0.1 Hz to 500 kHz. Applications: touch tone decoding. I think that might relate to telephone systems, keypads. Precision oscillator, frequency monitoring and control. So that's like radio, I think. Wideband FSK demodulation, ultrasonic controls, carrier current remote controls, communications paging decoders. And there is a simplified diagram which shows the pinouts. Maybe I should have covered the pinouts first. Okay, so before I continue, I've skipped down to page 19 of the data sheet, and I'll just try and cover the pinouts in my own words. So there's 8 pins, and pin 4 is VCC, and pin 7 is ground. So that's pretty easy to comprehend and understand. So VCC, it's recommended that a decoupling capacitor is used. 1 microfarad, I suppose, can be a ceramic capacitor. Okay, so I pulled up a capacitor chart, and 1 microfarad is here, and the code for that is a 105. And that's actually a larger size capacitor, so I don't know if you'll have the same problem as I had, but this is really found more in electrolytic type capacitors rather than ceramic ones. Well, maybe I stand to be corrected. I mean, here's a capacitor here that's a 105. It's listed as 1 microfarad. Anyway, I spent too much time covering that, but so pin 4 is the VCC with a 105 capacitor. Going back to ground is a decoupling capacitor. And then these 2 capacitors, this is a timing capacitor and a timing resistor, and these hook up inside to the internal oscillator. So choosing which capacitor and resistor will affect the oscillation, or rather the internal frequency. Pin 8 is sort of like your detector. Okay, so I won't spend too much time trying to explain this. I'll probably cover this later in the video I intend to make. But pin 3 is the input. So this is where you have your input signal. So maybe an audio jack coming from your computer, where you can maybe go to a website which plays a tone. You could plug this in, or maybe you could use a signal generator. Well, this is the input in. One thing I stand to investigate is whether this signal in requires the ground from that device as well, because it's not apparent by just having this input. So I wonder whether the signal in, you have to tie it to the ground. Okay, so for instance, here's an audio jack, and the top two tips, this one and this one, are the hot, or the audio signal, the positive, and then this is the ground. Maybe this is a better example because you've got the mono signal, so there's one signal, this is the positive, and that's the ground. So the input just shows the positive coming in, so I don't know if you ground the signal coming in as well. I am assuming you do. Anyway, these two pins here, 1 and 2, these two capacitors, which stand for output filter and loop filter. Output filter capacitor and loop filter capacitor. I stand to be corrected, but I believe that these capacitors set the band, the frequency band. I could be wrong. Well, as you can see, I have a little bit of learning to do. This one's a little bit mysterious to me at the moment, these two capacitors, as to what they do exactly. Pin 8 is like the output. So you get the input, and when you get a tone that matches that of pins 5 and 6, which is the internal oscillator, and when there's a match between the input and the frequency that the oscillator is generating, then the output will send a low signal, like a digital low rather than a high, and that would mean that your input frequency matches your internal oscillator frequency, aided by the resistor and capacitor you choose. This pin is a little bit interesting because you end up sending a VCC supply over to pin 8, and there's like a resistive load that you attach between. And I've seen some sample circuits that other folks have built, and this tends to be like an LED check light and a resistor. In the one instance, which I won't go into, they were using a 1K resistor. So anyway, what happens is when you get an input that's a match with the frequency that the internal oscillator is generating, then pin 8 will go low. And because of that, this will turn your LED light on if you've got one attached in this resistive load, whatever you call this. But if you're hooking this up to, say, an Arduino or something like that, I guess you could hook it up and have your microcontroller monitor when this pin 8 goes low. And that would make this integrated circuit a very useful chip. Well, anyway, Here's the pinouts. I'm not going to cover this. Kind of covered it already. But page 10 of the data sheet. Now, I always like to say in my videos that I'm not an expert. I'm not an engineer. I'm just a hobbyist. So it's possible I make some mistakes, or I stand to be corrected. Anyway, here's a simplified diagram. So I stand to investigate what a phase detector does, and what a Q phase detector does. This, I guess, is a voltage-controlled oscillator between pins 5 and 6. I'll just read this Wikipedia article into the video here on phase detector. A phase detector, or phase comparator, is a frequency mixer, analog multiplier, or logic circuit that generates a voltage signal which represents the difference in phase between two signal inputs. It is an essential element of the phased locked loop. That's worth studying. Oopsie. Detecting phase difference is very important in many applications such as motor control, radar, and telecommunication systems, servo mechanisms, and demodulators. A type 1 detector is designed to be driven by analog signals or square wave digital signals and produces an output pulse at the difference frequency. The type 1 detector always produces an output waveform which must be filtered to control the phase-locked loop voltage-controlled oscillator. So I have yet to fully understand all that. I guess a note to self to study this article on phase detection. But anyway, there's a phase detector on pin 3 and on pin 1. Well, you can see it as well as I can. And a Q phase detector. So that stands to be investigated by myself. Description: the LM567 and LM567C are general-purpose tone decoders designed to provide a saturated transistor switch to ground when an input signal is present within the passband. The circuit consists of an I and Q detector driven by a voltage-controlled oscillator which determines the center frequency of the decoder. External components are used to independently set center frequency, bandwidth, and output delay. Note to self to go back and restudy bipolar junction transistors, because I think that comes up as far as like the saturation point, but I won't digress. Okay, device information. Here's the part number. I guess it comes in the surface mount and the larger size as well. Personally, I have the larger size through-hole component. For all available packages, see the orderable addendum at the end of the data sheet. Okay, page 2 shows a table of contents for this data sheet, which I think is important to cover just briefly. Features, so we cover that. Applications, I guess that's contained in the same thing. Description, simplified diagram. Revision history. Device comparison table. Pin configuration and functions. Specifications. Parameter measurement information. Detailed description. Application and implementation. Power supply recommendations. Layout. Device and documentation support. Mechanical packaging, and orderable information. Okay, I think I'm going to skip reading the revision history. Okay, so there's a few different versions of this device, and here's a comparison table. It says that the LM567 and this other version are general purpose, and that there's this version, the LMC, and it's a lower power, current consumption, and double oscillator frequency. Okay, I covered this already, but I guess I'll say it again. Output filter capacitor, pin 1. Loop filter capacitor, loop filter capacitor, pin LPF of the PLL, stand to understand that better, input, this is the device input, VCC, pretty obvious, pin 8, device output, pin 7 is the circuit ground, pin 6 is the timing resistor connection pin, and pin 5 is the timing capacitor connection pin. Specifications, I won't cover this too much, but I guess this is the operating temperature. Supply voltage is 9 volts, although the recommended operating condition says 8.5 volts. Okay, here's the next page. This is page 5. It's saying the same thing again. Minimum 4.75 volts to a max of 9 volts. I really could be wrong about this, but here it's mentioning an input resistance. So what's that the input resistance of? Would that be the power supply? I don't think so. But is it pin 3, which is the input pin? Is that supposed to have a resistor on it? I really don't know. Or am I misunderstanding this? Whatever the input resistance is, the minimum is 18 kilo ohms with no specified maximum. I guess 20 kilo ohms is recommended. And for this version of the chip, it's roughly the same. Smallest detectable input voltage. Now this is important, because I was having some difficulty with some circuits I had built around the LM567, and I was having a hard time getting it to work, and I was using a signal generator, and I was wondering if the signal generator I was using had too much voltage or was too powerful. So I need to investigate that on my own. So without wasting too many words, smallest detectable input voltage. Well, I'm talking about input voltage, and then now we're talking about current. I'm a little confused. So 100 milliamps, I guess this is the test condition. So, okay, the smallest detectable input voltage using 100 milliamps as the current limit, I guess, and that would be somehow between maybe 20 and 25 millivolts RMS. So the limit is, let's just say, 20 millivolts is the smallest detectable input voltage, and the largest number of output input voltage under test conditions is 15 millivolts. Okay, I'll just try to read this quick just to get through this. Largest simultaneous outband signal to in-band signal ratio, 6 decibels. Minimum input signal to wideband noise ratio, test condition was at 140 kilohertz, minus 6 dB. Largest detection bandwidth, variation with supply voltage, test conditions 4.75 to 6.75, plus or minus 1 to 5 volts. I did notice that in some of my test circuits, when I was adjusting the voltage on my variable power supply, that actually affected the oscillator and the frequency which it oscillated at. Okay, I'm not going to read the rest. Okay, this is typical characteristics. I'm not really going to try and read all this. I guess this is according to temperature. I did notice a bit of frequency drift just by the sound of the oscillator. As I had my test circuit running and on, it does drift a little bit just by listening to it. This is talking about detection of bandwidth. Parameter measurement information. All parameters are measured according to the conditions described in the specification section. That was kind of like the temperature coefficients and the operating voltage. I'll read this again even if I've read it once already. Detailed description. The LM567C is a general-purpose tone decoder. The circuit consists of I and Q detectors driven by a voltage-controlled oscillator which determines the center frequency of the decoder. This device is designed to provide a transistor switch to ground output when the input signal frequency matches the center frequency passband. Center frequency is set by an external timing circuit composed by a capacitor and a resistor. Bandwidth and output delay are set by external capacitors. Here's the functional block diagram on page 8. I don't know about you, but this is almost getting too complex of a circuit for me to really easily comprehend. But they do have it broken down into the various pins. So right away here's pin 7, and it's really on this ground rail back to ground. Well, that is easy enough to understand. And likewise here's pin 4, and it's the VCC supplying everything. Somehow you can see that pin 1, I don't know if it's kind of interacting with pin 8. There was a simplified block diagram which kind of showed pin 1 and 8 were connected. Pins 5 and 6 were working together. So could this be some type of oscillator here? So this is digressing a little bit. Forgive me, I do that. But recently I was reading in a textbook about the Colpitts Oscillator, and the essence of it is down here. And you've got two capacitors and an inductor. I forget which one's variable. Well, anyway, I won't think out loud. I have a lot of learning to do. Anyway, next page is page 9, feature description, center frequency. The center frequency of the LM567 tone decoder is equal to the free-running frequency of the voltage-controlled oscillator. In order to set this frequency, external components should be placed externally. The components' values are given by frequency is roughly equal to, I'm not familiar with this so much, 1.1 divided by the timing resistor and the timing capacitor. Okay, sorry to jump around, but I've gone back to page 3 of the data sheet, which shows the pinouts, and once again the timing resistor is pin 5 and the timing capacitor is pin 6. Here's this page 19, which shows a layout example. So here's the timing resistor, timing capacitor, which is hooked up with a resistor. I think this could be a potentiometer, so it could be a variable resistor. And then pin 6 has like a, what's that, coupling capacitor? One of them. And here's on page 18, here's a test circuit. So it just shows some test values. So here's pins 5 and 6 with a resistor, and then the capacitor to ground. I guess this is a decoupling capacitor. But anyway, Notice that this is R1 and this is C1, pins 5 and 6. So here's this formula with resistor R1 and C1 on pins 5 and 6. Okay, so just for learning's sake, I think I'd like to take this formula and substitute some values in here based upon one of the test circuits that this data sheet shows. And I'll do that using the Paint program. So print screen. Okay, so I've got that on the page. Okay, and on page 18 of the data sheet, they have this AC test circuit diagram. So I'd like to use this as an example for a calculation. So print screen. Okay, looking good. Okay, so I want to focus on, make it green, R1 and C1. Here's the formula. Okay, so I've substituted the values for R1 and C1. There we go. And I'm assuming this is microfarad because that's the units of measurement that they use elsewhere in this circuit diagram. Oh, and I've chosen this 1.2K value for the resistor because this is a variable potentiometer, at least in a circuit that I built. Well, let's just make it one. I'll just put a little arrow through here. So that's a variable potentiometer. And let's just put it at a half. So 1.2K is half of this value. Okay, so I've got my calculator, and I plugged this into the calculator, and this is the result. I'll copy this. Okay, put that in here. Okay, so now I'm going to solve for the rest of the equation. So I typed in 1.1 divided by this number equals 2.7 repeating. So this ends up equaling 2.77.7. Well, would that be kilohertz? See, the problem might be that I didn't convert this to, say, just ohms and farads. Okay, so here's 0.0033 microfarad in farads. You get this exponential value. Okay, I'll try to do this here. 3.3 to the negative 9. So I really don't know how to do the math properly, because if you're not supposed to convert the units, and that's how the formula is supposed to work, then you get around 277 kilohertz, which actually makes sense. But if you go ahead and convert the units, it kind of ends up as this number. Well, I'm not a math magician. I guess I will point out that a 0.1 microfarad capacitor is recommended if you're building the circuit. So there's a bit more math, but as you can see by my math skills, I better not try it. Output filter. The output filter selection is made considering the capacitor value to be at least twice the loop filter capacitor. So I took this AC test circuit and I copied and pasted it and put it next to this this here. The output filter selection is made considering the capacitor value to be at least twice the loop filter capacitor. Okay, so ignore everything else. Pin 1 was the output filter capacitor. Pin 2 was this loop filter capacitor. So yes, this output filter capacitor is a greater value than the loop filter capacitor, and this holds true. Well, I forget where I was. I think I was somewhere here. Output filter. To eliminate undesired signals that could trigger the output stage, a post-detection filter is featured in the LM567C. This filter consists of an internal resistor, 4.7 kilo-ohm, and an external capacitor. Although typically external capacitor value is not critical, it is recommended to be at least twice the value of the loop filter capacitor. If the output filter capacitor is too the output filter capacitor value is too large, the turn on and turn off time of the output will present a delay until the voltage across the capacitor reaches the threshold level. That's worth pausing and studying. Loop filter. The phase-locked loop PLL included in the LM567 has a pin for connecting the low-pass loop filter capacitor. The selection of the capacitor for the filter depends on the desired bandwidth. The device bandwidth selection is different according to the input voltage level. Refer to this section, and the operation with this section for more information about the loop filter capacitor selection. What would we? Oh, more math. Logic output. The LM567 is designed to provide a transistor switch to ground output when the input signal frequency matches the center frequency passband. The logic output is an open collector power transistor that requires an external load resistor that is used to regulate the output current level. Die characteristics. Die layout C-step. Feature description, Table 1, die and wafer characteristics. I've paused and tried to read this and understand it. Maybe I'll just read it. Operation with voltage is less than 200 millivolts RMS. When the input signal is below a threshold voltage, typically 200 millivolts RMS, the bandwidth of the detection band should be calculated thus. So the bandwidth is 1070 to the square root of the input voltage divided by the frequency times the capacitance in percentage of the frequency, where VI is the input voltage RMS and capacitance is C2, capacitance at pin 2. You know, I did all those crazy math calculations before, and it's saying that the capacitance at pin 2 is in microfarads. So I'm thinking that this C2 value, you don't convert any units, you just keep them as they are. 2 microfarad, plug it into the formula. I forget if I said it or not, but this voltage input, I'm wondering if that's pin 3. I mean, here, pin 3. Well, I was just thinking, like, I guess if you've got voltage running through a capacitor, it's really decoupling, and so maybe the DC is eliminated, allowing the AC to go in. Okay, I will just read. Device functional modes continued. Operation with the voltage is greater than 200 millivolts RMS. Before it was voltage less than 200 millivolts RMS. Now its voltage is greater than 200 millivolts RMS, input voltage. For input voltages greater than 200 millivolts RMS, the bandwidth depends directly from the loop filter capacitance. Loop filter capacitance, once again, is this pin 2. I'll just start this sentence again. For input voltages greater than 200 millivolts, the bandwidth depends directly from the loop filter capacitance and free running frequency product. Bandwidth is represented as percentage of the free running frequency and according to the product of frequency of C2, it can have a variation from 2 to 14%. Table 2 shows the approximate values for bandwidth in function of the product result. This is table 2. So this is a product result. So this is the answer to a multiplication question. So when the frequency times C2 is 62 kilohertz microfarad, which is a new unit I guess they just came up with, the bandwidth is 2% of the frequency. Application and implementation. Application and implementation. Information in the following applications section is not part of the Texas Instruments component specification, and TI does not warrant its accuracy or completeness. TI's customers are responsible for determining suitability of components for their purposes. Customers should validate and test their design implementation to confirm system functionality. Application information. The LM567 tone decoder is a device capable of detecting if an input signal is inside a selectable range of detection. The device has an open collector transistor output, so an external resistor is required to achieve proper logic levels. When the input signal is inside the detection band, the device output will go to a low state. The internal VCO free running frequency establishes the detection band central frequency. An external RC filter is required to set this frequency. The bandwidth in which the device will detect the desired frequency depends on the capacitance of the loop filter terminal. Typically, a 1 microfarad capacitor is connected to this pin. The device detection band has a different behavior for low and high input voltage levels. Refer to operation with the different voltage levels. Alrighty, so once again I'm using the Paint program, as you can see here, so you can scribble on stuff. And I thought this was so complicatedly worded that I was going to try to break each sentence down to try to make sense of their cryptic explanation. Forgive my bad attitude. Okay, so the LM567 tone decoder is a device capable of detecting an input signal. So here's an input signal, and I guess it has to be within a certain frequency range. The device has an open collector transistor output, so an external resistor is required to achieve proper logic levels. Well, I guess this is the transistor output. I could be wrong. Well, I'll just have to read a definition into my video of an open collector. Open collector. An open collector is a common type of output found on many integrated circuits which behaves like a switch that is either connected to ground or disconnected. I cut it off. Let's look at the picture. Okay, internal to IC, so this is inside the IC, and the open collector is kind of just left open. I know. So I guess this here, this is like the open collector. So I'll try to draw it. So I guess in our case we have like this resistor, and I think we had a diode or something like that. How do you draw a diode? Oh, I'll just draw it like that. So, whoops. That's a diode. I know it's wrong. And then this is VCC. So I guess something we can't see is that inside the IC, it goes to ground. Okay, so I'm looking at the large schematic on page 8 of the data sheet, and it shows pin 8. So it's got, I guess this is internal. Everything here is internal. Here's the output, and inside it goes to ground. So this external resistor here, use this green. What does it say? So an external resistor is required to achieve proper logic levels. So I just created a note to self to play around with this resistor value to get a proper logic high or low on this resistor. Okay, so when the input signal is inside the detection band, the device output will go low, will go to a low state. The internal VCO, so the internal VCO, which I guess is connected between pins 5 and 6, I'll just try to read this out loud. The internal VCO, free running frequency, establishes the detection band, central frequency. So the VCO has a free running frequency, whatever it's currently oscillating at, I think, and it establishes the detection band frequency. Detection band central frequency. An external RC filter, I guess that's what this is, resistor capacitor filter. An external RC filter is required to set this frequency. The bandwidth in which the device will detect the desired frequency depends on the capacitance of loop filter terminal. The frequency band in which the device will detect the desired frequency depends on the capacitance of loop filter terminal. Typically, a 1 microfarad capacitor is connected to this pin. Okay, so here's an example of the touch-tone decoder circuit that they're using, and this C2, once again this is C2, pin 2. This C2 has a recommended 1 microfarad at 6 volts. And I guess C3, what did we learn? That has to be larger, at least twice C2. Typically a 1 microfarad capacitor is connected to this pin. The device detection band has a different behavior for low and high input voltage levels. Okay, I'll read that again. The device detection band has a different behavior for low and high input levels. Input, again, I think we're talking about the input on pin 3. So, depending on the input frequency, whether it's above or below 200 millivolts. So, in other words, the output is going to be different. It'll have different logic levels based upon the millivolts of the input. That's how I read that. I could be wrong. Okay, so I was on page 12. I just broke this down in the Paint program, and now it's going into some specific schematic diagrams. So this is the touch-tone decoder. That's interesting if you want to play with your telephone, I think. And then here's some specs on values for your supply voltage. So this is 20 millivolts for the input voltage range. So that's falls under this category. Voltage is less than 200 millivolts. So I guess depending on whether your voltage is greater or less than 200 millivolts will depend on how you design your circuit. I think that's what it's getting at. And so it throws some math at you again. Detailed design procedure. So yes, they're talking about how to design your circuit, and they're giving this formula. To calculate the timing components for approximated desired central detection frequency, the timing capacitor C1 should be stated in order to calculate the timing resistor R1. Typically, for most applications, 0.1 microfarad is used for C1. This is C1. Bandwidth. Detection bandwidth is represented as a percentage of frequency. Is that output? I don't know. It's a 0. It can be selected based on the input voltage levels. For voltage input, when it's less than 200 RMS, this is the math formula you use. when it's greater than 200 millivolts, refer to Table 1 and Table 2. This was Table 2. And this was Figure 5. Output filter. The output filter selection is made considering the capacitor value to be at least twice the loop filter capacitor. C3 is greater or equal to C2. Application curve, so they're talking about pin 3 and pin 8. Okay, so this might be telling us something. So when pin 3, here's the input. So here's pin 3. And when the frequency starts to go faster and faster, then pin 8 is going to go low when it hits the frequency detection. Okay, I paused it and I studied it, and I have to say I don't understand it. Oscillator with quadrature output. Here, pin 7 doesn't appear. I'm assuming it's grounded. And pin 1 doesn't show up here, which usually pin 1 was this output filter capacitor. That doesn't show up on this oscillator in quadrature output. And pin 3 is permanently grounded, so that's the input. Why would you permanently ground your input so the signal frequency is always 0? Well, then you read the description, connect pin 3 to 2.8 volts to invert the output. Well, now I'm confused because that's not what the picture says. The picture says to hook up pin 3 to ground. So I don't know, I'm confused. This picture does not correspond with this one, I don't think. Or maybe it does, I don't know. I guess it does, quadrature output. So I guess if you hooked up, so I did that, pin 3 now has 2.8 volts. Why would you just sync power directly to ground? Would you maybe put a capacitor in here? Something like that, maybe? I don't know. I think I'm going to stop reading here. Just really not understanding what it's saying. Like, I've heard of a prescaler. A prescaler is an electronic counting circuit used to reduce a high-frequency electrical signal to a lower frequency by integer division. That kind of looks like what's going on here. So I don't know if these are just circuits set up to make use of the oscillator. Maybe you're not even using input detection anymore. You're just like offsetting the phase. I don't know if that's correct to say that. And maybe using this as a type of prescaler. Just a guess. If anybody's watching and they know, please correct me. Precision oscillator drive, 100 milliamp loads, and AC test circuit. Stay tuned. I may or may not show this. I actually built this on a breadboard, and I intend to show it off on camera, demonstrate how it works a little bit. I'm having trouble. Well, I won't explain now. I'll read this. Page 19, Power Supply Recommendations. The LM567C is designed to operate with a power supply up to 9 volts. It is recommended to have a well-regulated power supply, as the operating frequency of the device could be very high for some applications. The decoupling of power supply becomes critical, so is required to place a proper decoupling capacitor as close as possible to the VCC pin. And that's what they're showing here. Layout guidelines. The VCC pin of the LM567 should be decoupled to ground plane as the device can work with high switching speeds. The decoupling capacitor should be placed as close as possible to the device. Trace lengths for the timing and external components should be kept at minimum in order to avoid any possible interference from other closed traces. Here's the layout example. Okay, this is worth clicking on. There's links. There's community support. Do these links still work? And the rest of the data sheet seems to go into pick and place reels for, I guess, manufacturing in the surface mount size. So it's not really that interesting to me. Okay, thank you very much for watching. I hope it's been helpful, and have a good day.